So in this, what will be the final short session here, we're going to look at solver numerics and HPC. So this is something that affects everybody, and again, has brought some generic benefits. So one of these is the way we detect poor quality cells. So we know that a few bad cells can be really bad in a simulation, can even cause divergence. And Fluent has had some poor mesh numerics testing criteria, which allows you to do clever things with those cells. So now you can not only detect based on poor mesh quality, but also on bad gradient calculation, and include those cells in those that are marked for treatment as poor mesh. And at poor mesh, typically you would either revert to doing a first order solution, so upwinding, or if it's really severe, a zeroth order solution where you basically just do a bit of local averaging around that cell and put the average value in. The correction form of the numerics has been made the default. So what this means is that instead of working with variables which are the value at the new iteration level and the value at the old iteration value, we now work with the old value and the delta, so the correction, so that by doing that, this can avoid accumulation of rounding error, and therefore it can allow you to run more calculations in single precision. And on modern chips, running single as opposed to double can give you a very large speed up, almost 50% in some cases. So that is on by default now and is the standard. There's an option now to treat solid motion in, for example, heat transfer in solids, actually directly rather than by doing things in a multiple reference zone. So basically, instead of having to set up a multiple reference zone, you can now switch on this rotating option, and that puts additional terms in the equations in the solid, which will deal with this. You can actually convert to this new method with a GUI option if you want, and this is going to improve performance, improve solver time, etc. Improved anisotropic mesh adaptation. So that's really improving how you can split up your boundary layers when you want to refine them. The adjoint solver has got a new method of smoothing the mesh out, and that's using something called the radial basis functions, which avoid many of the problems you have with either some sort of direct interpolation or some polynomial mesh. So the mesh gets much more evenly distributed. The adjoint solver now has support for non-constant material properties, which we know is really important, in, for example, in high-speed aeroflow. So you can now apply the adjoint solver to a wider range of problems. And there's improved diagnostics. So if it's not solving, we can get more information out to find out what the source of the problem is. Some high performance computing, which again affects really most people. So there's been some linear solver performance increases. I mean, they're not spectacular, they're average 5%, but on some problems they can be as high as 40%. File read-write performance has improved. So now that HD5 is the standard, they've been able to go in and work on the problem cases that were actually slowing down or were not speeding up well with this new format. And so that's been addressed in this release. The inbuilt compiler that you can use with Windows has now got support for C++ as well. And so that can deal with your C++ UDFs. You can also, now it will also pick up the fact that if you've got a local compiler, you can use that. but if you want to use the inbuilt one, it'll go to that last. So there's some automation in choosing compilers. MPI has been updated to the 2019 release, which is giving improved performance out of the box. Okay, so that's the end of my numerics at HPC. So again, moving to this latest release will give you some benefits just because the code will run faster, both in a raw sense, and also the HPC will be improved. So I hope that 2021 R1 is something you're now dead keen to use, and you upload that and get using it on your jobs from now on. Thanks for attending these this series of presentations. Bye.